Hello, my name is Samuel Rodriguez. I'm a senior at Florida State University, Panama City campus. This video is a presentation on the project I did for COT 4401, also known as top 10 algorithms. What I did for this project was make a JavaScript based simulator for the A-star pathfinding algorithm. So this is what you see on the screen right now. When the user brings it up, they're presented with instructions here on the side, just a few hints to help you navigate through the simulation, and there's a little color code chart down here so you kind of know what's going on. You have gray for walls, green is our start square, red will be our goal square, blue is the path that the algorithm is finding, and pink is all the cells that were visited during the calculation of the path. So you can kind of see right now as I'm clicking on these individual cells that'll toggle it into a wall, and it's running its simulation in real time as I click. It's figuring out the path from the green cell over here to the red cell over here. Over on the right hand side there's a few controls. There's a run button, and once you click it'll toggle to a clear path, and you can click that, it'll clear it out. There is a clear walls button over here that will clear all the walls that are currently on the simulator. Below that we have two sets of navigational controls. The green corresponds to the green start square. So if you start clicking that, you'll see that it's changing the position of the start square. And I had that also running the simulation so you can kind of see as you're moving the start and the goal, what's happening with the path. Now, because the grid I have here is pretty large and clicking on squares can take you a long time to do to develop some walls, I set up a few scenarios here under the setups button, which will give you different scenarios. There's setup 1, put your start up here in the top left and the goal down here in the bottom right. Number 2 brings you to the middles. Number 3 is still kind of in the middle, but I brought him in, shorten the distance between the two. Now once we get over here to step 4, we'll start seeing some different walls. So this is a cave looking structure here, this U-shaped, sideways U-shape, so that you can kind of see from the start cell to the goal, to go into this structure. It's not really going to be the shortest path because you're having to backtrack to get out of it. Setup number 5 is just kind of a double walled feature with a diagonal from the start to the finish. And number 6 is the crazy one. This is going to have all kinds of walls just randomly anywhere. So we can run the simulation on any of these setups, and you'll see that the algorithm develops the path through the I guess it kind of looks like a maze, all the different walls we have set up with this, and it's calculating the shortest distance because there's multiple ways through here. Now what's fun to do is you can take where you see this thing going through certain walls and certain paths, you can kind of block it and try to manipulate the path. Like right here, it seems to be coming through a pinch point right here. So if I turn that wall on, this algorithm now has to take a different path because that one's blocked. So you can keep doing this, and what you can eventually force is this situation right here where there's no path. You've got all these pink squares but no blue line because there is no path. from this start to this finish at this point. And then you can, in a similar sense, start untagging walls to see if you can find a path back, and the algorithm will figure that out for you. So we'll get back to all that in a minute. Down here is a heuristic type. The method I used was the what we call a Manhattan distance. I'm going to use this close one here. Let me get them a little closer together. Alright, so this Manhattan distance, if you look at each one of these cells and think of it as like a city block and you're walking to get there, a Manhattan distance from here to here, you're taking 1, 2, 3, 4, 5 cells, because you're going over 1, 2, 3 and going down 2. It's kind of an easy way to determine an estimated distance, especially in this grid setup, because the way I have it running is you can go up or down or left or right. It's not going to take diagonals. So there was a couple different variations to this Manhattan distance. One is what I call the nudge, and what's happening is if I click down here, you're going to see it kind of change paths here. But what happens is it's taking 1/50th of a calculation to add a little bit of variation between squares. Because pure Manhattan distance, you'll have a lot of equal square distances. And what this nudge does is kind of push them a little farther so that there's a decimal equivalency that's being measured against each other. So, you know, instead of, what do we say, this was 5, you might have a 5.0000639. And that just kind of helps it narrow it down when it's choosing which of these directions it wants to take. And these close together, you can kind of see small variations. A big difference you'll see is if we go to setup 1, you have the start up here in the top left and this down here in the bottom right. And if I run the simulation, you're going to see a diagonal line straight to the goal, but it's not going diagonal, it's going over, down, over, down, over, down. And the difference you're going to see, I'm going to click it back over to Manhattan distance, and what's going to happen is it's going to be looking at it like how many squares over do I have to go and how many squares down. And what happens with a big wide open space like this is that more squares are going to be visited so it can figure out the path, and you'll see quite a difference. I'm going to click it and then it's going to, the calculations are going to take longer, and it's a little bit of a noticeable difference. So I'm going to click it now, and boom, there it goes. So now it's visited every square in this grid to get a path over. And you get kind of a freeze there because you see that there's obviously way more calculations. There's way more pink than let's say the nudge. So there's quite a difference. You can see the difference in visited squares, which, I mean, speed, less calculations, we're going to be a lot faster. The other heuristic type that I have down here, it's still based on the Manhattan, but this is a cross product, and what it's doing is taking the vector cross product of the path from your start to the goal and the current square that it's calculating to the goal, and seeing where they're crossing. And what it's doing there is just kind of keeping in line with where it wants to go. I'm going to load up a different scenario here so we can see some difference. I think it's number 4. Alright, here's our cave structure, our sideways U. If I run this right now, I'm going to run it on Manhattan first, and you'll kind of see it's up and over, and it's visited a fair amount of squares before it got to the goal, before it figured out. Now if I switch it to, now this is, in the other one you're going to see some of these other nudge and cross product were way better than Manhattan, but sometimes the Manhattan isn't always the best. I mean, these other ones aren't always the best. So I'm going to switch it over to the nudge. And here, with the nudge, we have a problem. Because we are going in. And then we think we're headed to the goal. And then it figures out it's in. And it has to start backtracking all the way around. So in this situation, this is not the shortest path, obviously. Because we're subtracting this and adding this, which is quite a bit. Let's see what the cross product does on this. Much better. So the cross product one still visits these squares but realizes that it's inside of a structure, so it's going to go up, it's going to go over, and then start stepping up towards the goal, which is pretty neat. The other double wall, so again, here we go. I'm going to click the Manhattan, and it's going over, goes up and over, and down to our goal. You can see all the squares it's visited. I'm going to click it over to the nudge, and let's see what happens. Same thing, same path. There's a little bit of extra, say 2 squares extra from here because it's headed towards. And cross product, now here's where the cross product got messed up. The cross product was headed towards this goal, then it hit the wall, so it went around it, and then up. I'm going towards it again, but what happens, there's another wall, I have to go up. So this one is costed here 2 for all of this, which isn't very fun. I want to see. Let's go back to the nudge cross product on this setup, and just to kind of show you some of the start and finish controls, how it affects what you're seeing on the screen. I want to show those off a little bit. Here I'm taking the goal, and we're going to start moving it around, and you can see what's happening. Each click it's moving, and there it reaches a point where it's faster to go around this way. Even on the nudge one, it does some wacky stuff because it's still trying to head towards that goal. So kind of fun to play with these and just see how the algorithm reacts to it. Let's try another one, the double wall with the nudge. So on the nudge, it's kind of following that path, but still hitting that wall. Cross product, same thing, but it's searching out more. And Manhattan, good old Manhattan regular with no kind of modify to it, just trucking along and going down. And the reason it's kind of set up that way is because when it's searching for the lowest F-score, the lowest cost, in this grid-based system, the algorithm that I wrote is starting here, which I just call north. It's looking north, it's looking east, it's looking south, it's looking west. So it's that same pattern. So when it's comparing the F-scores, the north, if the north is the shortest, but it's also the south is the shortest by the same distance, when this algorithm's going around, I've set the north first as the lowest, and then it's searching the other ones to find one lower. If it doesn't find one lower, then it's going to keep the original one, which could be changed with less than or equal to, but I just kept it in that order for more predictable results. So for something like this, it's outperforming the nudge or cross product just because the East is had the lowest score versus some of these other ones, and that's what was, even if it was tied, it was still the lowest. So it favors starting north, going east, and then south, and then west as the last. So you could have a dead tie, and north would win first, east will win second, and south, and then west. So I don't know. There's definitely some work I'd like to do in the future with honing in that algorithm, trying different variations, because it's very interesting to me. I mean, there's pretty much every video game that people play has some sort of I guess you'd call artificial intelligence. The bad guys you're playing against, the cars you're racing against, it's all got to be controlled by a computer. And the more realistic these algorithms are to help those computer opponents find paths through the game worlds, the better. I mean, they're gonna. If we go back over here to this right here, and let's compare a couple. Starting here, green guy trying to get to the red guy. A real basic opponent, computer-controlled opponent, would just go straight and over, and that's what this regular Manhattan is showing us. The nudge is a bad example. You wouldn't want this in your video game where this guy trying to get to this guy is going in here and seeing that it's a wall too late and having to backtrack around, because a person looking in that could see 3 walls would know that there's no way out, so that you need to go north. So I like the cross product because it kind of like looks over there and sees that there's no way out and goes north and over. So that's, to me, is the most realistic one for this scenario. This right here, if you're once again playing a game, green guy trying to get to the red guy, Manhattan just straight over, just kind of a mechanical sense to this person going over, versus the nudge, the cross product. And this one may look a little bad, but in that context, in that scenario, them going to the wall but staying near the edge and kind of looping through here kind of makes sense. And let's see. Then in the maze one, let's do these kind of, the maze you kind of just making your way through. You don't see a lot of difference. I don't know if there's any difference in the path, because you're kind of limited. But what you do see a difference is how many squares it takes for this thing to visit before it finds a path. The Manhattan is kind of a big pink blob behind there. Looks like the nudge is going to be the best as far as visiting the least amount of nodes before it finds a path, which is pretty good, I think. So this demonstration, this simulator, is online. Feel free to check it out. It's at right now it's at www.samcodes.com, and it should be on the main page there. Go check it out, play with it, break it. I mean, I'm sure that my implementation of the algorithm is not 100% correct. While I've definitely learned a lot about it, I've in no way or by no means claim to have perfected it. I'd like to go back and work on it some more. It's very interesting to me, and I plan to get into the gaming field eventually once I get a little experience under my belt with some of these other jobs, because I think there's a good future in the gaming industry. It's already a multi-billion-dollar industry right now. But anyways, get on here, check it out. Keep an eye on my website as I start developing little web games. I'm going to be posting them on there at samcodes.com. Thank you guys so much for listening.